This video is for Module 1, Part 7, and includes the ear infection case study. All right, let's go ahead and get started. So the ear infection case study is a comparison between breastfeeding and bottle feeding, and whether or not that has any relationship on the rate in which an infant gets ear infection. So there are certainly advantages and disadvantages to both types of feeding. There's a video that discusses this topic. This video is for the Jamaican population. In this video, they also mention risk factors such as age, sex, presence of secondhand smoke, etc. And the study that we're going to look at also takes into consideration variables such as age, sex, socioeconomic status, I believe, is one of them. So I'll let you watch that video. That gives kind of a good highlight of what we're talking about here. Also, I was able to find on the internet a pamphlet that talks about ear infections in children. This pamphlet was provided by the Department of Health from the state of New York. And one thing that I just wanted to point out on this pamphlet is that they make a statement on that pamphlet that suggests that breastfeeding appears to lower an infant's risk of ear infections. And those words have been chosen carefully, I believe. It does not say that breastfeeding will lower an infant's risk of ear infections, but they use the word appears. The data from our case study is going to provide a similar finding to this. All right, so let's talk a little bit about the ear infection case study. So a common symptom of ear infection in young children is the prolonged presence of fluid in the inner ear. The hypothesis has been proposed that babies who are breastfed for at least 1 month may build up some immunity against the effects of this condition. A small study of 24 pairs of babies is set up where the babies are matched on a 1-to-1 basis according to age, sex, socioeconomic status, and types of medication. One member of that match paired is breastfed, and the other baby is bottle fed. The primary focus from this study is the duration of fluid in the middle ear after the first episode of ear infection. So the question of interest here: is there a difference in the duration of ear infection between breastfed and bottle-fed babies? Some study design considerations. So let's talk a little bit about those. The idea of matching babies in this study is an important design consideration that was made. Matching the babies before conducting the study will allow for better comparisons to be made. So for example, they matched on age. So age is known to influence the ear infection rate in children. So age should be used in the matching process. So the older a child gets, the larger their ear canal gets, and it's easier for that fluid to get out of that middle ear. So it's not going to be fair to compare a 2-month-old to, say, an 8-month-old, because that ear canal of the 8-month-old child is bigger and going to allow for that fluid to get out more easily. Sex is another criteria that's going to be used in the matching. So they're going to want to compare males to males and females to females. Socioeconomic status is something that they took into consideration in their matching. And that's just synonymous with affordability of and access to medical care. So if your baby is sick, are you able to seek treatment when needed? So we're going to want to compare babies that are similar across socioeconomic status as well. And then medications was also used as a matching criteria. If a baby was on any type of medication, they want to match that against some other baby that might be on that medication. Couple of definitions. The response variable is the primary outcome or measurement of interest in an analysis. It's also referred to as the dependent variable or the Y variable. A confounding variable is a variable that cannot be delineated from another variable when attempting to establish a relationship with the response. So let's talk a little bit about the confounding variables here in the context of this example. The purpose of the one-to-one matching of the babies in this study, according to age, sex, socioeconomic status, and medications, will help alleviate these variables from acting as a confounding variable. That is, if these variables are thought to potentially influence the outcome, which is the duration of fluid in the middle ear, then these variables should be considered when designing the study, so that fair comparisons can be made between the breastfed and bottle-fed babies. When these variables are taken into consideration, we can be more confident that if a difference is found, the difference is due to the type of feeding and not some other variable. So we're going to want to compare babies that are similar in age and sex, socioeconomic status, and medications in this study. And that's what they did. They matched on all four of those variables. Let's talk a little bit about the study outcomes. The primary outcome measurement from this study was the duration of fluid in the middle ear after the first episode of ear infection. The results from 24 pairs of babies are provided below. Now, when we make these comparisons, we're going to want to do these within each pair. So let's talk about that for a minute. So this 20 right here just represents how many days did this particular baby have fluid in its inner ear. Now this baby is from pair 1, and this baby was actually a breastfed baby. We want to compare that 20 against this 18 over here, because again, these babies were paired up or matched on those criteria up above: age, sex, socioeconomic status. So these two babies right here are going to have similar ages. They might both be males. They might both be from low-income families. Okay, this pair down here is going to be similar as well. So we're going to want to look at these within each pair or do these head-to-head comparisons. Now, as I stated, this is the number of days that they had fluid in their inner ear. So in this head-to-head comparison here, 18 is the one that won out. The bottle-fed baby actually won out there. So what I did over here on the right was just identify which pair did better. Okay, so in that head-to-head comparison, 18 did better, so I've highlighted that. And then I've identified over here on the right that the bottle-fed baby actually did better. Right, because this is the number of days that they had fluid in their inner ear, so we want these values to be small. In that second pair, it was 11 versus 35. In this pair, we can see that the breastfed baby did better, and that's been indicated over here on the right as well. So we're going to do that all the way down. We're just going to identify how often did the breastfed baby do better and how often did the bottle-fed baby do better. We also have this situation of a tie. So here I have 7 days for the breastfed baby and 7 days for the bottle-fed baby. I'm actually going to ignore that tie because when I'm doing this two alternative forced choice methodology, I can only have two outcomes. So we'll just ignore that tie situation there. So then I just need to count how often did each one of those win out. So there are 16 times in which breastfed baby did better than bottle-fed. So how many yellows do I have highlighted? Okay, there's 16 of those. And how often did the bottle-fed baby do better? That would be 7 times. Talk a little bit about our simulation model. So again, as stated above, the recorded measurements were actually the number of days that they had fluid in their middle ear. And I had to move that data or identify who did better in each one of those situations. So if I want to apply this 2AFC methodology, I need to get this down to 2 outcomes. And I've done that by just identifying whether or not the breastfed baby won out or the bottle-fed baby won out. Now, the simulation model is going to be set up under a situation of no difference. This is going to be similar to simulating a situation of no discrimination, or talking about the staring example, simulating a situation of no ability. So this is analogous to the other examples that we've done. If there is no difference between breastfeeding and bottle feeding, then we'd expect breastfeeding to win out about 1 out of every 2 times, or about half of the time. So if we go back up to our table, if there was no difference between breastfeeding and bottle feeding, in this who did better column, I would expect about half of them to be bottle fed and about half of them to be breastfed. So that's under a no difference situation. That's what I anticipate the outcomes to be over there in the right-hand column there. So the necessary information for building or constructing my simulation model, number of pairs under consideration is going to be 23, because again I got rid of that tie so that I could have only 2 outcomes. And then the likelihood or chance of breastfeeding doing better under a situation of no difference is just going to be a 50-50 situation. The expected value is going to be just computed by multiplying the number of trials by that probability. So take 23, multiply it by 0.50, which is going to be 11.5. So I should expect about 11 or 12 times the breastfed baby to do better than the bottle-fed baby. Now, let's recall the question of interest for this investigation is whether or not a difference existed between breastfeeding and bottle feeding. So if we go back up here to our original question of interest, is there a difference in the duration of ear infection between breastfed and bottle fed? This question is not asking whether or not breastfeeding is better than bottle feeding or the other way around. It's simply asking, is there a difference? So under the no difference situation, the expected outcome there is 11.5, so that's where my reference distribution is centered at. Again, I don't know how much inherent variation exists. I need to build or construct that simulation model to figure that out. But I do know that if I'm really high on this number line, then breastfeeding is going to be better. So if I go back up to my table again, and let's suppose that all of them on the right-hand side here are breastfed 1 out. So in every single situation, the breastfed baby did better than the bottle-fed baby. How that's going to be indicated on my number line is the number of times that breastfed baby did better is going to be really high. Now, if the number of times that breastfed baby did better is really low, so let's say it's close to 0, then that's going to indicate that bottle-fed babies are going to do better. So in that situation up here, let's suppose that I don't have hardly any yellows over here, or maybe I only have 1 yellow over here. So most often the bottle-fed baby did better. That's going to indicate that I should bottle feed our baby. So both ends or both extremes of this reference distribution provide evidence for my research question or my question of interest. And this type of investigation is called a two-sided analysis, where both sides actually provide evidence for my research question. So real quickly, the relevant values for our simulation model: smallest possible value is going to be 0, largest possible value is going to be 23. Label is going to be the number of times breastfed babies did better. My expected outcome is just going to be 11.5, so halfway up that number line. This is a two-sided analysis, and the study outcome is 16 here. The number of times that breastfed baby did better from our study is 16. So when I did those tallies here, you can see that that's 16. Now, we haven't talked about this yet, but I could build a reference distribution for the number of times that bottle-fed did better. Okay, so if I was going to use the number of times bottle-fed did better, okay, it would still be centered at 50-50. The implications of the extremes would be different. They would have to be reversed. But my study outcome, if I were to track number of times bottle-fed did better, my study outcome here would actually be 7 instead of 16. So when you're building a reference distribution, you can do it for either one of the outcomes. You're going to get exactly the same answer. A real quick comment for how can I identify whether or not I have a two-sided situation. So when the research question or the question of interest contains the phrase, "Is there a difference?" So if that's part of your research question, then most likely both sides of the reference distribution are of interest. So that's usually a pretty good giveaway that I'm doing a two-sided analysis. Okay, so here's setting up the reference distribution. I'm going to, probability of success or probability of heads here is going to be set to 0.50. The sample size or the number of tosses is going to be set to 23 here. The number of repetitions, I think down below I obtained 1,000 repetitions, so if you wanted to put 1,000 in there you could, or 10,000 or 500, it doesn't matter. You also, when you're doing this example, are going to want to indicate that you're doing a two-sided analysis. So down in the lower left-hand corner, we're going to want to make sure and click the two-sided button down there. So that's unique about this example here. Let's talk about the application of the outlier rule then. So when I have selected the two-sided, what that's going to do is actually attempt to find cutoff values on the lower end and the upper end of the distribution. So here I've set this up with 1,000 repeated iterations. Okay, I have specified on the lower part of the two-sided, as I said up above there. I'm attempting to use a cutoff value of 17. So what the app is going to do under a two-sided situation is count the number of dots at 17 and above or at 6 and below. So it's going to count the number of dots on both sides. And it's telling me over here that I have 16 dots, it looks like, at 6 or below. And I also have 14 dots here at 17 and above. 16 plus 14 is 30. 30 divided by 1,000 is 0.03. So 17 looks like, well, 17 and 6, I guess, look like reasonable cutoff values for this problem. If I take my cutoff values and move them in a little bit, so instead of at 17, if I move that in a little bit towards 16, what that's going to do on the other end point, or the other end of the distribution, is move that into 7 now. So the corresponding value for 16 on the other end of the distribution is 7. So when I use 7 and 16 as my cutoffs, we can see that that's a little bit too large. Again, what I'm shooting for here is a 5% level, and it's at 8.8%. If I go the other direction, if I move this out to 18, so if I slide this out to 18, then my lower end point is going to have to go down to 5. Okay, and I think that's going to be too conservative. I think up here in the table above, if I use a lower limit of 5 and an upper of 18, I only have 0.009 or 0.9% of the dots. Again, I'm shooting for about 5%. So of these three different cutoff values here, it looks like 6 and 17 seem to be the most reasonable. It's slightly under the 5% level, but it's pretty close. So when determining whether or not I have an outlier in this distribution, I'm going to use the values of 6 and 17. Let's talk about evaluating the evidence then. So the question of interest, again, is there a difference in the duration of ear infection between breastfed and bottle-fed babies? This is what my schematic is going to look like. Again, I'm simulating a situation of no difference. My upper cutoff is going to be 17, and my lower cutoff is going to be 6. If I'm at 17 or above, I'm going to be considered an outlier. And it's going to provide evidence that breastfeeding is doing better. On the other hand, if I'm at 6 or below 6, I'm also going to be an outlier in this distribution. Again, suggesting that I have a difference, but indicating that bottle feeding might be doing better. My study outcome here is at 16. So again, not quite enough evidence to be an outlier. My cutoff is at 17. I'm actually at 16 here. So with a study outcome of at 16, I do not have enough statistical evidence to suggest that I have a difference between breastfeeding and bottle feeding. It's close, but it does not exceed or would not be considered an outlier. Okay, I think I provided 5 questions here for you to answer. I will let you answer those and submit your outcomes. And then when you go back and review, you'll be able to see my answers for each of those. All right, that does it for Module 1, Part 7. Thank you.